So in this session, let's talk about the demo boards available for the iCE40 Ultra Plus family of devices. There are a number of available boards out there, but Lattice website will support the following three boards for sale. The first board is a mobile development platform, and with that there are 4 iCE40 Ultra Plus devices available on this board, 4 distinct devices very specifically targeted for specific demos, and there's a number of other devices available on this eval board for demos such as face detect, mic aggregation, graphics, display demos, and so on. So each one of these iCE40 Ultra Plus devices can perform very specific demos connected to the specific devices for that purpose. Now, the next available board is the iCE40 Ultra Plus breakout board, and this one is a very simple board with the iCE40 Ultra Plus device in the middle, the power and clock external devices hooked up, and the FTDI USB chip hooked up for programming purposes. But all of the IOs on this device do go to IO pads, and the only other available device on this is an RGB LED that is connected to the dedicated 3 RGB LED pins of iCE40 Ultra Plus device. And finally, there is the Arduino board, which is a very low-cost FPGA board available from the following website, gnarlygray at .atspace.cc for $7.99 or $9.99 or $15.99, different versions of it available. And this board also contains only the iCE40 Ultra Plus device with the power and RGB LED devices. And all of the IO pins do go to specific pins for the Arduino type applications. So we're going to look at the Arduino board and the design that's available from the GitHub. We've downloaded the design on this desktop for the version 2 of the Arduino board. That design does require a iCEcube2 tool to run. So we're going to open up the iCEcube tool. The basic interface of the iCEcube tool contains a design section where all the project, the synthesis, place and route flow, constraints, everything resides on this left side. The middle side or the right side does contain all the windows associated with each one of the processes that you would open. So since the project is already on the desktop of this computer, we're going to open it. File, open project. It was downloaded into a folder called RGB LED blink with a specific date, and within that folder there are 2 subfolders, one of them called RGB, and that's the one we want to open. This would contain the actual project. The iCEcube2 tool project file has the extension .project. And we're going to double click on that file to open the project. Once opened, on the left side we do get the option to start the synthesis, and that is the first thing we want to go through on a given project. If we click on design files, you'll notice there is only one Verilog file. If I double click on that Verilog file, the source code for a RGB LED blink is listed here. We're going to simply run a synthesis in order to let this tool know what the project is all about. Synthesis step requires double-clicking on Run Simplify Pro Synthesis option. Once that's done, the tool is now aware of this design, and the next thing to do would be to run the mapping or importing of the input files in this iCEcube2 project. Once you get a check mark next to the import PNR input files, now the tool is aware of this design. It knows what the pins are, what the functions of those pins are. So at this point, it would be necessary to look at the constraints or pin constraints of this design and see if the pins that were generated in the design are placed correctly to specific pins. Because the design is to drive the RGB LED pins on this device, it will require those pins to be assigned to very specific pins. Those pins are locked. Those are dedicated pins on the device, in this case red, green, and blue. Now, if we were to run this project in the next step, run placer, the tool will automatically make the pin assignments for us. So we're going to run the placer. And then next we can run the router to route the design. At each step of the way, if there are any errors or warnings, they will be listed in the output section on the right side. And finally, we're going to run the generate bitmap. This generated an actual bitmap that can be programmed into the device. Now, if we were to go back to the pin constraint screen, the pins 39, 40, and 41 were automatically placed for us because those are the dedicated pins in this particular device for the RGB function. So the tool recognized that the Verilog file, the Verilog source file, was calling out for those 3 pins. Each pin has the specific function of the RGB block behind it. So it automatically knew that those pins need to be assigned to pins 39, 40, and 41. And that's how this particular instantiation for the RGB driver calls out for those dedicated pins. And so the bitstream generated here can be now downloaded into the Arduino board, and the LED, RGB LED should be blinking because the function called out here is making use of the high-speed oscillator, high-frequency oscillator in the chip. It's a 48 megahertz oscillator, and also that oscillator is being divided down via a counter, and a very specific count is being used to blink those RGB LEDs or drive the PWMs for the RGB LEDs. So the next step would be to bring up the Diamond programmer to program the board. So we're going to start Diamond programmer. This is the standalone Diamond programmer, and the first thing it checks is whether or not you have a cable hooked up. You could click on detect cable, and if it finds the cable, everything is okay. You can click OK at this point to create a new project from a JTAG scan. Now, since our iCE40 Ultra Plus devices do not have a JTAG interface, the Diamond programmer will come up. It will detect the cable, but it will not detect a device because there is no JTAG scanning happening at this point. So you'll see a failure saying failed to scan board, scan failed. This is normal. This is only for the iCE devices that do not have a JTAG interface. At this point, you can simply go and select this generic JTAG device and you can drop down the menu and go select the iCE40 Ultra Plus device. So we're going to manually select the density, which on Arduino board is a 5K LUT device. So the iCE40 Ultra Plus 5K is the selected device. The next thing to do would be to double click on this cell under operation. This is the cell that determines what operation you want to perform. If you double click on that, you do get the device properties dialog box. In this dialog box, you have the option of programming the device in 3 different ways. First one is just the internal SRAM programming. That way, you're temporarily programming the device, but as soon as the power is turned off, that configuration will go away, because this is only programming the internal SRAM. The next one is to program the actual one-time programmable non-volatile configuration memory, and this one you would only use in cases where you have a production board. It is a code that is well vetted out, working code, and the device can be programmed once, and that program will always boot the device. And finally, in our case, we're going to use the SPI flash programming option, because on the Arduino board there is a external SPI flash device that can be used to reprogram the iCE40 Ultra Plus FPGA. We do have a bit stream from the iCEcube tool we generated, and that bit stream resides in a subfolder under the project, RGB project. Under the RGB implement folder, there's a subfolder called SBT. Under that, there's another subfolder called outputs, and under outputs, there is a subfolder called bitmap. This is where 3 files reside. Every time a new bitstream is generated, these 3 files do get generated. The first file is a bin file. My preference is to use that file to program the device. There's also a hex file, another format of the bin file, and this can also be used to program the device. And thirdly, there is a Intel hex format bit file that could be used for other options, such as an external PROM to be used to program the device. But in our case, we're going to use the bin file. We'll click on open. And next thing to do would be to select the SPI flash available on this board. It has to be the exact SPI flash vendor and part number in order for our tool to be able to program it. In this case, there is a WinBond chip which is not available through the standard SPI serial flash options of the vendors. We do need to use the SPI serial flash beta option, and there is a WinBond as vendor, and under that there is a W25Q32 device available, which is a 8-pin SOIC. There is other packages available, but in our case it's an 8-pin SOIC package. I always like to click on the load from file button just in case the actual data file size from the bin file wasn't loaded. The device, the tool will load that particular number of bytes, and the start address and edge address allow you to load this particular configuration in different sectors of the SPI flash. This particular case, we do need to start from hex address 0. There are cases where multiple configurations can be loaded in different sections of the flash, and that is possible by selecting the different sections. But for the actual boot section, we do need to load it from hex 0. We're going to click on OK. And finally, all that needs to happen is the program button needs to be pressed to actually start the programming function. So we're going to press that button. We'll see status on the output window of what's going on. The tool went out, found the cable that is connected to our device, and it did go through programming cycle, and at the end came back with the successful message, which means the board is programmed successfully, and we do see the LED blinking on the board, indicating we have a successful programming. If the power of the board was turned off and turned back on again, the device boots from that external SPI flash we just programmed. There are multiple other functions available under operation. If we double click on that dialog box again, there is some operations that you could perform. One of them being erase all, and this goes and erases the external SPI flash. To do that, you just click on that and click OK and program again. This should erase, and the LED should stop blinking on our board, which it did at the moment. And once the board is fully erased and connected back again to verify that the SPI flash was truly erased, and yes, the LED does not come on. So we know that we successfully have erased the external SPI flash. This comes in handy when you're debugging things and want to make sure that a new code is loaded into the FPGA rather than the old code constantly causing issues. So now let's talk about what's going on under the hood with the programming options that we saw in the Diamond Programmer. There are several things that are possible to do. The iCE40 devices and the Ultra Plus in our case do have a number of interfaces. One is the SPI flash interface, so an external SPI flash can come in and program the FPGA. The other interface is the interface we use with our download cable to program the device, or an application processor can be used with some GPIOs that can be toggled to mimic the SPI interface and program the device through the application processor. So that interface do connect to both the SRAM memory space, and it also connects to the MVCM memory space. The MVCM is the non-volatile configuration memory, and the SRAM space is available in all of our FPGAs where we load the configuration temporarily. This is the space where after power down, the configuration goes away. So on the next power up, the device would either program from the MVCM, program through an application processor or our download cable, or program through the SPI flash interface. Now let's talk about the actual flow chart of what is happening when the device is powered up in order to load the configuration. This is the device configuration control flow. After the power up, there is a CDone bit that is set to 0. So we know that the device is empty, there is no configuration. And the first thing to do is to check if the power on, reset signal is released. This is basically a signal internally generated in our FPGAs when a good power signal is or level is reached. Our sensors basically tell the state machine inside that the power is good, the level is good. Go ahead and generate a reset power on reset signal. This power on reset signal gets the state machine and everything, the engine going for the programming. So once that is done, we check a particular pin. This is a dedicated pin in every iCE40 device called the reset B, and we're checking to see if that pin is high. If it is high, we continue on to program the device. If it is low, that means somebody is holding that pin low to delay the start of the configuration. And this is useful in cases where you do need other devices to come up before the FPGA is up and running. So once that pin is high, we jump into the next state where we look for the chip select signal coming in from the SPI interface. If an application processor or a microcontroller externally is holding the chip select high, then we know we want to program the device from this interface, the SPI interface. So the device will start the configuration through the SPI peripheral interface, and once that is completed, it sets the CDone signal to high, indicating the programming is done, device is configured, and we at that point go ahead and check the C reset signal again, and we wait in that state until the C reset is pulled low. If it is low, we jump back and start the whole process of reconfiguring the device. This C reset signal indicates whether or not we want to reload the configuration or we want to come back in and program the device again. So if the SPI interface is not detected, if the chip select is not detected, if that is low, then we continue on. If that is high, we continue on to the next stage where we check and see if our non-volatile configuration memory is enabled for configuration. There is an internal bit that gets set when the MVCM is programmed. Once that bit is set and we're in this stage, we know that we want to load from the MVCM memory. And that non-volatile configuration memory gets activated, the configuration gets started, and we go through that whole series of setting the C done once the configuration is done and checking the C reset B again. If the MVCM is not programmed, then we continue on to program the device through the SPI flash PROM, external SPI flash. And that requires the SPI flash to be connected and ready to program the FPGA. If the SPI flash is not connected and wasn't available for programming, then we continue on and stay at the C reset stage where we are constantly checking to see who's going to program us next. And that's the basic flowchart of the iCE40 device.